Okay, so hello everyone, welcome back. We're gonna take a look at the chapter 4 for today. So the first section on chapter 4 that we're gonna talk about is gonna be polynomial function and models. Okay, so section 4.1, we're gonna talk about polynomial function and models. So let's take a look at the definition. What is a polynomial function? Okay, so there are many different kinds of function. The constant, the linear, and quadratic function that we study from the past, right, are part of the larger group of function called polynomial function. So how can we recognize if a function is a polynomial function? A polynomial function P, so polynomial function P is given by P of x equal n times x to the power n plus n minus 1 times x to the power n minus 1 plus a sub n minus 2 times x to the power n minus 2 and plus dot dot dot. We're going to go all the way down to a1 times x to the power 1 and a0. So an minus 1, an minus 2, a1, a0s are real number, and the exponents are whole number. Okay, so we're gonna base on this definition over here to determine if we have a polynomial function. The exponent must be a whole number. Okay, so whole number is mean that 0, 1, 2, 3, 4, 5, and etc. Okay. So the first non-zero coefficient, an, is called the leading coefficient. The first non-zero coefficient, an, is called the leading coefficient. So an is the leading coefficient. The term an times x to the power n is the leading term. So we have the leading term, we have the leading coefficient. The decrease of the polynomial function is n, because we have x to the power n is the term with the highest power on the variable x. So that's why the polynomial has a decrease of n. So in order to determine the decrease of the polynomial, you have to know the leading term. In the leading term, we have the leading coefficient. And then the power of the variable x in the leading terms, it can help us to determine the decrease of the polynomial. Okay. So that's just the definition, how we recognize a polynomial function, what's in the leading term, what's in the leading coefficient, and decrease of the polynomial. So let's apply those definitions to answer the first question right here. Determines if the following function are polynomial function, find the leading term, the leading coefficient, and the decrease of the function if exists. Okay, so let's take a look at the first example over here. Part A is that's a polynomial function. So we have 2 times x to the power 3 minus 5 times x to the power 2 plus 4x and then minus 5. So you have to double check the power on each of the variable x over here, right? So we have 3 is a whole number, 2 is a whole number, x to the power 1 or x is a whole number, and the last time doesn't have the variable x. So yes, this is a polynomial function. Okay, so yes, this is a polynomial function. Okay. So after we determine if a function is a polynomial function, the next thing that we're going to do is find the leading term, right? So the leading terms is going to be the term with the highest power. So you have to look for the variable with the highest power. In this case, we have x to the power 3 is the term with the highest power on the variable x. So that's why the leading terms are going to be 2 times x to the power 3. So the leading terms is 2x to the power 3. So in the leading terms over here, the coefficient 2 is the leading coefficient. So we have leading coefficient. So the leading coefficient is 2. Okay. Now the next part of this question is what is the decrease of this polynomial function? So the decrease of the polynomial function is the decrease of the variables in the leading terms, right? The decrease of the polynomials is the decrease of the variables in the leading term. So take a look at the leading term over here. We have x to the power 3, right? So that's the power 3. So the decrease of these polynomials is decrease of 3. Decrease of the polynomials is 3. Okay, so that's the first question over here. So you determine if we are given a polynomial function. After we know that we have a polynomial function, we're going to determine the leading term, leading coefficient, and decrease of the polynomial. Okay, so that's example A. Okay, now example B. So take a look. So part B is over here. Let's give it a try. Okay, so we're gonna work together. So over here, let's see if this is a polynomial function. Okay, so let's take a look at the function g sub x equal 2 over x plus 5. Okay, so this function g sub x, they have the term 2 over x right here. So I'm gonna rewrite that terms over here if you know the exponential rule from the past. So the function g sub x, we can rewrite that 2 times by 1 over x plus 5. Okay, and then that function g sub x over here, we can also rewrite as as whenever you have the terms 1 over x, I can rewrite that as x to the power negative 1 plus 5. Okay, so you have to rewrite the term over here in the form a times x to the power n. Okay, so a times x to the power n. Okay, so now let's take a look at the power n. So in this case, we have 2 times x to the power negative 1. So negative 1 is as a whole number. No, negative 1 is not a whole number. It is an integer, so it violates the definition over here. The exponent must be a whole number. In this case, we have the exponent in negative 1. That is not a whole number. So this is not a polynomial function. So no, this is not a polynomial. Okay, so because this is not a polynomial function, so you don't have to find out the leading term, leading coefficient, and the decreaser. Okay, because this is not a polynomial function. Okay, so similar idea over here, you can try part C and part D. Okay, so I'm gonna give you the answer just in case, right? So you can complete the answer over here. So for part C, we have h of x equal the square root of x minus 5. This is not a polynomial function. Why is it not a polynomial function? Let me help you with this. So h to the power, h of x equal the square root of f. We can rewrite as x to the power 1/2. And then we have minus 5, right? Okay, and then 1/2 is not a whole number. So once again, because 1/2 is not a whole number, so that's why this is no, this is not a polynomial function. So part C, that this is not a polynomial function. Okay. Now part D is going to be your turn to practice over here. So I'm going to give you the answer first over here. So we have this part D. Yes, this is a polynomial function. Okay, now you're going to finish this question. Let's find out the leading terms. What's the leading coefficient? And what's the degrees of this polynomial? Okay, so what's the leading term? The leading terms is going to be the term with the highest power. So we have negative 3 x to the power 6. That's the term with the highest power. So that's going to be the leading term. So negative 3 x to the power 6. That's the leading term. Leading coefficient is going to be the coefficient of the leading terms, right? So we have negative 3 is the leading coefficient. What's going to be the decrease of this polynomial? So we have the leading term has x to the power 6. So the decrease of this polynomial is going to be 6. Okay. So this is just a few practice questions based on the definition of polynomial function, how we identify the leading term, leading coefficient, and the decrease of the polynomial. So when you do your homework question, there will be some similar question. Okay. So now let's move it on to the next topic that we're going to talk about in this section 4.1. Okay, so the next thing that we're gonna talk about, we gonna take a look at the different kinds of graph of the polynomial function. Okay, so this is the polynomial function. This is the example of some different graph of polynomial function. And then this is the graph of non-polynomial function. Okay, so polynomial function, right here we have 4 examples for different graph. Those are the graph of polynomial function. And then for those 4 over here, those are the graph of non-polynomial function. Okay. So when comparing polynomial function and non-polynomial function, we can take a note over here that the graph of the polynomial function are continuous with no horns, no breaks. They are also smooth. Okay, so when you're observing the graph of the polynomial function over here, you can see that when you go from left to right over here, it's going to be continuous, no horn, no break, and a very smooth curve. There's no sharp corner. The domains of the polynomial function is the setup on real number. The domains of the polynomial function is the setup on real numbers from negative infinity to positive infinity. Okay, so the domains of the polynomial function from negative infinity to positive infinity. Okay. Now let's moving on to the leading term. So after we know how to identify the leading term from a polynomial function, and after we know how to identify the leading coefficient from a leading term, now let's talk about what is the purpose of the leading terms of it. Can we have any conclusion relate with the polynomial after we know the leading terms of the polynomials? Okay. The behaviors of the graph of the polynomial function as x become very large, it means that when x approaching positive infinitives, or when x become very small, it means that when x approaching the negative infinitive. It referred as the end behavior. Okay, the end behaviors of the graph of the polynomial. So we talk about the end behaviors of the polynomial function, the graph of polynomial function. The leading term of the polynomial function determine the end behavior. Okay, so if you know the leading terms of the polynomial, we can determine the end behaviors of the graph of the polynomial function. Okay. So let's observe in the even and then the odd over here, right? So when we talk about the polynomial function, there are only 2 possibilities that we can classify the polynomial function based on the leading term, right? So after we know the leading term, we can identify the decrease of that polynomial. And then after we know the decrease of the polynomial, we can classify that as an even number or an odd number, okay? So this is a few examples of the polynomial with the even degree, and then this is some examples of the polynomial function with odd degrees. Okay, so what's the summary? What's the conclusion that we might have after observing those graphs over here? So let's take a look at the leading term test. Okay, so the leading term test is going to help you to determine the end behaviors of a graph of a polynomial function. Okay. So if an times x to the power n is the leading terms of the polynomial function, then the behaviors of the graph as x approaching positive infinitives or when x approaching negative infinitive can be described in one of the 4 following ways. Okay. So now let's talk about the case when the decrease of the polynomials is an even. Okay. So after we know that the decrease of the polynomials is an even number, now you have to take a look at the coefficient, the leading coefficient. If the leading coefficient an is more than 0, so you can say that it's gonna going up on the left and it's also going up on the right. So they both raising up to the left and then to the right. If n, the power or the decrease of the polynomial is even and the leading coefficient is positive. Now, when n is an even or when the decrease of the polynomial is an even and the leading coefficient an is negative, then you can say that it's gonna going down on the left and going down on the right. They both going down on the left, and then on the right, if the leading coefficient is less than 0. So this is the case when n is even or the decrease of the polynomial function is even. How about when we have the decrease of the polynomial function is odd? Okay, so if the decrease of the polynomial function is an odd number, n, now let's double check the leading coefficient an. So if an is more than 0, then it's gonna go down to the left and it's gonna go up to the right. It's going down on the left hand side, it's going up to the right hand side. When the leading coefficient an is less than 0, it's going up on the left and it's going down on the right. Okay, so the leading term test of it is only give you the conclusion based on the end behavior. It's not gonna tell you the middle portion. Yeah, the middle portion of the graph is not determined by this test. So that's why you can see that in between, it's not gonna give you any conclusion. We only focus on the end behaviors of the polynomial function. Okay. So you have to know the decrease of the polynomials and you have to know the leading coefficient so we can determine the end behavior based on this table or this summary, the leading term test. Okay, so the next thing we're gonna do is we're gonna do some practice question related with the leading term test. Okay, so let's take a look at example 2. Okay, so using the leading term test, determine the end behaviors of the following polynomial functions. So all of them are polynomial functions. So before we can determine the end behavior, you have to give me the leading term, right? So what is the leading term? Okay, so the leading term will be, what is it for part A? So the leading term for part A is gonna be 3x to the power 4. After we know the leading term over here, we can identify the leading coefficient. So the leading coefficient is 3, which is more than 0, right? This coefficient 3 is which is more than 0. What is the decrease of this polynomial? What's gonna be the decrease of this polynomial? So we have the leading terms is 3x to the power 4, right? We have x to the power 4, so the decrease of this polynomial is 4. And 4 is an even number, okay? So we know that the decrease of the polynomial is an even, and we know that the leading coefficient is 3 more than 0, then based on the table. So we have n is an even and we have a and e more than 0. So it's gonna go up to the left and going up to the right. Okay. So it's gonna be, you can say that's gonna raise it up. So they both going up on the left side and on the right hand side. Okay. So that's how we're using the leading term table to determine the end behavior. Okay. Now part B, let's try it together, everyone. Okay. So once again, before we can determine the end behavior, we have to identify the leading terms. So what's gonna be the leading term for this given polynomial function? So negative 2x to the power 2 minus 2x plus 7. So the leading terms are going to be negative 2x to the power 2. After we know the leading term, we can find out the leading coefficient. So the leading coefficient is going to be negative 2, and we know this is less than 0. Now we're going to find out the decrease of polynomial. So we have negative 2x to the power 2. So the decrease of this polynomial function, a2, is an even number. 2 is an even number. Okay, so what's going to be the end behavior for this polynomial function? Okay, so we have the leading terms in negative 2s, and we have decrease of the polynomials in 2 is an even. So let's take a look at the table we have earlier. So we have n is an even because we have the decrease in 2, and we have the leading coefficient in negative 2, which is less than 0. So it's going to going down to the left and going down to the right. Okay. So we can say that this function will going down to the left, going down to the right. Okay, so that's gonna be the conclusion for the end behaviors of this polynomial function part B. Okay, now part C and part D is gonna be actual practice for you, everyone. Let's give it a try. Okay. Okay, so we just talk about the leading coefficient test, right? Leading term test. It's gonna help you to determine the end behaviors of a polynomial function. Okay. Now let's move it on to the next topic on this section. We're gonna talk about the zeros of a polynomial function, finding zeros of a polynomial function. So what does it mean by zero? So zeros, it means that for what values of the variable, the function will be zero. That's what I mean by find a zero, okay? So if C is a real number, is a real zeros of a function. If C is a real zeros of a function, then f of C will be zero. Okay, so it means that when you plug in the input by C, the output of the function will be zero. That's what I mean by zeros of a polynomial function. Then you can say that the ordered pair C comma 0 gonna be the x-intercept of the graph of the function. Okay, so the 0 is gonna be the x-intercept of the graph of a polynomial function. Okay. So we're gonna base on this definition to determine if some number is a zeros of a polynomial function by just substitute that values into the function and do the calculation to see if the final answer or the output will be zeros or not. If the output is zero, then that number is a zeros of the function. If the output is not a zero, then that number is not a zeros of the given polynomial function. Okay. Now let's do some practice, right? Use the substitution to determine if 2, 3, -1 are zeros of the following function. Okay, so they're gonna give you 3 numbers over here for you to double check. So we're gonna try the first one over here first, which is okay, so we're gonna try the first values over here when x equal 2. Okay. Okay, so we're gonna try this value when x equal 2. That determines if x equal 2 is a 0. Now, the second value is x equal 3. And now the third one is x equal -1. Okay. Now we're gonna try the first two together and the third one is gonna be yours. Okay. So now x equal 2, if you want to determine if 2 is a zeros of the given polynomial function, we're gonna substitute, so we're gonna replace the input x by 2 and do the calculation to see what's gonna be the output. So now we're gonna evaluate f of 2. So f of 2 means we're gonna substitute on of the input x by 2. So we have 2 to the power 3 minus 3. 2 to the power 3. Oh, I think I make a typo over here. Just see, oh, that's fine. Power 3, then that's fine. Plus 2, because x equal 2 plus 6. Okay. Okay, so now let's complete the calculations over here, everyone. Let's see. So we have 2 to the power 3 is 8, 8 times 2 is 16. Okay, so we have the first calculation is 16 minus 2 to the power 3 is 8, 8 times 3 is 24, and then plus 2, and plus 6. Okay, so let's see what's going to be the final answers, everyone. You might use a calculator. 16 take away 24, plus 2, 6. So the answer is 0. Okay, that's good. Okay, so we have the output gonna be 0. So f of 2 is equal to 0, then yes, 2 is a 0. So your conclusion is gonna be yes, 2 is a 0 of the given polynomial function. Okay, that's how you show your works over here. Just do the calculation or evaluate f of c. And if f of c is equal to 0, then c is a zeros of that polynomial function. Okay. Now let's try the second value together. So over here, everyone, f of 3. So we can evaluate f of 3. So gonna be 2 times 3 to the power 3 minus 3 times 3 to the power 3 plus 3 and plus 6. So 3 to the power 3 is 27. 27 times it by 2, so 54. Minus 2 to the power 3 is 27. 27 times 3 is going to be 81. Minus, oh, that's a plus, 3 plus 6. Now let's find out the answer over here. So we have 54 minus 81 plus 3 plus 6. So the answer is going to be negative 18. Okay, so negative 18. So we can see that negative 18 is not 0, right? So negative 18 is not 0. So when you plug in x equal 3 into the given polynomial function, the output is not equal 0. So you can say no, 3 is not a 0. 3 is not a 0 of the given polynomial function. So that's the second value. Now the third one is going to be your turn to double check, everyone. When x equals negative 1, let's determine if negative 1 is a 0 of that given polynomial function. Okay, your turn to try it. Okay. Now we're going to move it on to the next portion. Okay, the next topic that we have on this section 4.1. Okay, so let's see what is it. Oh, okay. So we're still talking about the zeros over here, but now it might be something new. Okay, different than what we did earlier. Find the zeros of the following function. Okay. So once again, this question asking you to find out one of the zero that we have for this given polynomial function. So what they actually asking us to do. So really, they asking us to do the f of x equals 0. You have to find out for what possible values of x or what are the possible values of the input x to make the function equal 0. And we know f of x, right? So f of x equal 5 times x minus 3 to the power 3. And then x minus 1. Okay, equals 0. So we're going to solve in this related equation. 5 times x to the x minus 3 to the power 3, x minus 1 equals 0. Okay, so on the left hand side over here, we have a product, right? So anyone remember how we did with this equation? So we have a product equals 0. So we have something that we learned from the previous course. It's going to be 0 product property. Yeah, so using 0 product property. Okay, you might Google this. Yeah, let's see what is it, right? So a product is equal 0 if and only if at least one of the factor will be 0. That's either 0 product property. A product is 0 if and only if at least each of the factor will be 0. Okay. So we have a product equal 0, so we're gonna set each of them equal 0. So the first factor is 5, right? Because we have 5 times, but this is a 5. 5 not gonna be 0, so you don't have to worry about that factor because this factor is not gonna be 0. How about the second factor? The second factor we have is x minus 3 to the power 3. We're gonna set that factors equal 0. Or we have another factors over here, which is x minus 1. We're gonna set that factors equal 0 also, and we're gonna solve in those related equations. So we have x minus 3 is equal 0, right? So if x minus 3 is equal 0, you can say that x minus 3 must be 0, right? Or I'm gonna copy the second, x minus 1 equals 0. Okay. So if x minus 3 is equal 0, then x equal 3, right? Or x minus 1 equals 0, then x equal 1. So those are we have 2, 0 for this given polynomial function. Okay, so we have the first zeros is 3. The second zero is -1. You can double check that on the graph of the given polynomial. So if you're going to graph in this polynomial function using your calculator, then you can determine if it's true, right? So we know that x equal 3 is a 0 and x equal 1 is a 0. So those going to be the x-intercept we're going to get. So x-intercept is the point where the graph of the function cross the x-axis. So you can double check. So the first intersection point right here with the x-axis is going to be -1. And then okay, yeah. Oh, I copied the wrong one. Okay. So then now it should be -2. My apologies, that's not consistent. So let me change it to make it consistent. Yeah, okay. There you go. It's a typing. It's a typo when I copy that. Okay, so we have two zeros over here, x equal 2 and x equal 1. So you can observe in that by take a look at the graph over here. So when x equals 0, that's the first x-intercept. When x equal 2, is the second x-intercept. Okay, but let's take a look at this. Okay, so for the first x-intercept, when x equal 1, the graph is going to be crossing, right? It's going to be crossing the x-intercept, but for the second x-intercept over here, look like it's going to be tangent or going to be touching the x-intercept, right? It's going to be touching the x-intercept. It's also touching and it's going to be cross. It's cross and touching, right? Okay. It's cross over here, right here. Okay. So that's something that we're going to talk about later. Okay. Okay. So we have this is the power 3 and this is the power 1. Those power will affect the touching and crossing. Okay. So by observing once again, you can say that x equal 2 is the first x-intercept right here, and then x equal 1 is the second x-intercept. Okay. And we have the power 3 and this is power 1. Okay. Now let's take a look at part B over here. We're gonna try it together, maybe, right? Okay. So same kinds of question. We need to find the zeros of this polynomial function. Okay. So once again, finding the zeros, it means that you're gonna set the function equal 0. And what's the function we are given? Negative x minus 1 to the power 2, and then x plus 2 to the power 2 is equal 0. Okay, so it's going to be similar with the last question, last practice question, last example. We're going to use the zero product property, using zero product property. We have a product equals 0. It means that at least each of the factor will be 0. Okay, so we have the first factors is x minus 1 raised to the power 2 is equal to 0, or we're going to get the second factor, x plus 2 to the power 2 is equal to 0. So we have x minus 1 to the power 2 is equal to 0. It's only true if x minus 1 equal 0, right? Or x plus 2 equal 0. Now, if you solve in this related equation, x minus 1 equals 0, then x equals 1, or x equal -2. So for part B, we have 2, 0, or we have 2 x-intercept, right? So the first x-intercept is 1 right here, and this is the x-intercept right here. And the second x-intercept is -2. Okay, so let's take a look up the intersection point over here. What happened between the graph and the x-axis over here? So for the previous case, you can see that at the intersection point over here, or at those x-intercept, the graph is gonna crossing the x-axis over here. But for this case, it's not crossing, right? It's only touching. It's gonna be tangent, touching the x-axis. Okay. So what's the conclusion that we have so far? So the only thing that we can determine for crossing or touching or tangent is gonna base on the power outside so of those factors. Okay, so even multiplicities and odd multiplicity. Okay, so we talk about this property. It's mentioned the multiplicity, so it means that how many times that 0 got repeated. Yeah, so multiplicities of a 0. So if x minus c to the power k is gonna be more than or equal 1, is a factors of the polynomial function px, and x minus c to the power k plus 1 is not a factor, and if k is an odd number. So if the power k is an odd number, then the graph gonna cross the x-axis at the point c comma 0. So if the multiplicity k is an odd number, then when you graph in that polynomial function, it's gonna cross the x-axis at the point c0. If the multiplicity is an even or k is an even, then the graph is tangent or touch to the x-axis. It's gonna be tangent to the x-axis at the point c comma 0. Okay. So based on the multiplicities over here, we can determine if the graph of the polynomial function will cross or is it going to be tangent with the x-axis. Okay. So if it's even, it's going to touch or tangent. If it's going to be odd multiplicity, then it's going to be cross. Okay, so that's another properties of the polynomial function that you might need to keep in mind when we talk about the graphing of the polynomial function. Okay, so this is the multiplicity, even, odd. Okay, so now let's find out, let's apply the summary, the multiplicity that we have on the previous page. Let's answer this question. Find the zeros of the following function. Okay, so finding the zeros of this function. So finding the zero, it means that you have to set up the function equals 0. F of x equals 0. Now we have x to the power 4 minus 4x to the power 2 plus 3 equal 0. Okay, so this is a trinomials, everyone. You might need to go back and review. Is it possible that we might factor in this? Yeah. So this is a trinomials equation, right? So we have 3 terms. So on the left hand side over here, it will look like quadratic actually, but it's not directly quadratic, but it's gonna be quadratic in the form. So if some of you guys took intermediate algebra, you might know how to deal with this kind of equation. Okay. So I might using the factoring over here. So you might using the factoring for trinomial. You might need to go back and review that factoring for trinomial. So x to the power 4 minus 4x squared plus 3 is equal 0. I'm gonna use the AC method that you might see that from the past. A is equal 1, B is equal -4, and C is equal 3. I'm gonna use in this method that maybe some of you guys know us from the past, hopefully. Okay, let me draw this real quick right here. We call this either AC methods or the diamond methods. Okay, so we have 1 times 3 is 3. Okay, so let me put the number 3 right here. And we have this in -4. Okay, so 1 times 3 is 3, put the number on the top, and this is -4. Okay, so now I'm looking for 2 numbers. When you multiply them, it's equal 3. When you add them up, it's equal -4. There are 2 numbers. When you multiply them, it's gonna give you 3, but when you add them up, equal -4. The number are, what are they? We have -3s, and we're gonna get -1. So -1 times -3 is equal +3. -1 plus a -3 is gonna give you -4. Okay. So after we find out that 2 numbers, we can factor in this trinomial. But watch out, this is x to the power 4. So we have x to the power 2 minus 3, because we have that's a -3. And then it's gonna be x to the power 2 minus 1. Okay, equal 0. Okay. Now, there is something that we can factor in more. So obvious, everyone. So we have x squared minus 3. Okay. So if you know how to factor in this, you might factor it more. If not, then we can solve it directly. Okay. So just assuming that maybe you don't know how to factor in more. So now I'm gonna using the zero product property. So the first factors, I'm gonna set them equal 0. So x to the power 2 minus 3 is equal 0. Or we're gonna get the second factors over here. X to the power 2 minus 1 equals 0. Okay, now let's solve this equation, everyone. Okay, so x squared minus 3 is equal to 0. So we're gonna get x squared is equal to 3, or x squared is equal 1. Okay. Okay, so we have x squared is equal to 3 and we have x squared is equal to 1. Now we need to find out the solution of x. So we're gonna using the square root property or the principle of square root. Yeah, using the, we're gonna take the square root, taking square root. Okay. So when you take the square root of both sides over here, make sure that you don't forget the plus and minus. So we have x equal plus or minus square root of 3. Or we're gonna get x equal plus or minus square root of 1. Okay. So square root of 3, we cannot simplify anymore. We can't simplify anymore. So that's gonna be the answer. So x equal plus or minus square root of 3. Or what is square root of 1? So square root of 1, they're gonna give you 1, right? So x equal plus or minus 1. Okay. So there are 4 zeros for this polynomial, right? So there are 4 zeros plus or minus square root of 3 and plus or minus square root of 1. So there are 4 zeros that we have. Yeah. So there are 4 zeros. X equal plus or minus square root of 3. And then x equal plus or minus 1. Okay, so there are 4 zeros right here for this given polynomial function. Okay. Okay, now part B is gonna be your turn to try, everyone. Let's find out the zeros of this given polynomial function. So I'm gonna give you a hint for this question over here. You might factor by grouping. Okay, so f of x equals 0. So we have x to the power 3 plus 3x squared minus x minus 3 is equal 0. So factor by grouping, it means that we're going to group the first 2 terms in one group and we group the second 2 terms in another group. So when you take a look at the first 2 terms over here, so x to the power 3 plus 3x squared, they has a common factor, which is x squared. X squared times x plus 3. Okay. Now let's take a look at the second group. We have negative x minus 3. So they both have a negative. So I'm going to factor in the negative. So x plus 3 equals 0. Now we can see that we have x plus 3 is a common factor, right? So we're going to factor it more. So we have x plus 3 times it by x squared minus 1. Equal 0. Now, if you remember this special product over here, x squared minus 1, right? We can even factor it more. So x plus 3 times x minus 1 times x plus 1 equals 0. So we just done factoring of this polynomial function. Now you're gonna keep going and finish this question. Let's find out what are the 0 for this part B. There are 3 0 for this question B. Okay. Now, the last portion of this section 4.1, we're going to talk about some models, polynomial models. Okay, polynomial function have many uses as model in science, engineering, and business. So let's take a look at this application right here. A dog lifespan is much shorter than of a human. The qubit function right here. So we're going to use in this qubit function to name what is it right here. So let's take a look of the interpretation where X is the dog age, the age of the dog in years, approximated the equivalent human age in years. Estimate the equivalent human age of dog that are 3, 12, and 16 years on. Okay, so we're gonna use this function to estimate if what's gonna be equivalent human age in terms of year if the dogs have the age of 3, 12, and 16. Okay, so what we're gonna do? So actually, we're gonna plug in x equal 3. Okay, that's the first thing. Because that's the first calculation, they're asking us to do x equal 3. And then we're gonna do the second things, x equal 12. And now the third one, we're gonna do x equal 16. Okay, so you might need a calculator for this substitution over here, everyone. Okay, so I'm gonna copy this function over here. It's a lot of number. Okay, so I'm gonna copy this function. And I'm gonna replace the input over here by 3. So every x right here, I will just replace it by 3. Okay, so now you're gonna use in your calculator to find out the answer. Okay, now and then similar idea when x equal 12. So you're gonna use in the same function over here, and we're gonna substitute x equal 12. So the input will be replaced by 12. So make sure that you have the calculator to try these questions, everyone, so you can get the answer easier because the number doesn't look like it. Nice. And same thing over here for the third case over here, x equals 16. We're gonna use in the same function, but now the input equals 16. So this is the application. So in this case, we're gonna using the polynomial function given, and we just evaluate it with some given values of the input x. Okay, so you're gonna use in your calculator to find out what's gonna be the answer for one of those function with the given values 3, 12, and 16. Okay. Okay, so this is the conclusion of section 4.1, everyone. So let's take a break. Make a stop over here, come back and do your homework, and we're gonna talk about 4.2 next time.